in line with the purpose of the lecture series. So basically, well, I'm a former practicing architect that is now a researcher, and I will talk about what I think this topic of artificial intelligence means for the profession. So it's not primarily a research talk, although I will share a little bit about my research. It's more about, yeah, basically I will share with you my opinion, my insights, what the recent developments AI mean for the profession. And so, let's start. I'm not sure if you have seen this. So this is a study from Goldman Sachs about the impact of AI on the economy in the coming decades. And so what they're looking at here is how many work tasks in different industries can potentially be automated by AI. And so what's very notable that here the first one is of course office and administrative support. That's kind of logical. Everything that is paper shuffling is very amenable to AI. And then the second one is legal, because legal you could think is basically a more fancy form of paper shuffling. And then we have architecture and engineering. Pretty remarkable at 37%. And so the remainder basically will be devoted to exploring what that might be. Like what is the 37% and what does this mean? And so to answer this, we look into what is going on with AI at the moment. And then of course there is what is very getting a lot of attention sort of in the design discourse of architecture is this generative AI topic. Might be, I think, all familiar with Midjourney, and you've also seen all these images on Instagram and etc. And so what does this generative AI mean for design? And then I'm claiming there is another type. Oh, this should be AI, of course, right? Supportive AI. So I'm claiming there's another ways to use AI that is not so much about generating designs, but supporting what designers do. And then finally, also talk about what AI means for practice. And so, what's going on with AI? So, as I said, it's not really a research talk, so I'm going to start a little bit from the beginning. So, AI is very old. It starts in the 50s. So, we have this big field of AI with different methods, which tend to be about trying to sort of identify rules in what human experts do and feeding that in the computer so that the computer can do certain tasks. Then in the 80s, we had this big moment of machine learning, where the big discovery was instead of trying to teach the computer rules, we just give data to the computer and then the computer can infer some rules. And so it's a more indirect method. And so now we are living like the third wave of deep learning. So the deep learning basically is machine learning with neural nets. Right? So it's in a way, this is a particular case of this machine learning approach where we feed data into the neural net and then we can have certain outcomes. And I go into it a little bit more why we can see all the wonderful things that we are seeing. So a different way to look at this is to say, okay, on the one hand, there was this classic old AI that was programmed by humans, that is symbolic and rule-based. So symbolic basically means that I already give some concepts to the computer, right? So I could say I have the concept of man, and I have the concept of Napoleon. Napoleon is a man, and he lives in a country, and the country is France. So these concepts that are human meanings. That is symbolic, right? While if I just feed a lot of text into a neural net, then it will detect sort of the patterns in this text, but it will not actually have the meanings. And I'll show you in a few minutes an example what the consequence of that is. Right? So on the one hand, we have the classic AI that is symbolic and rule-based, and then the new AI, machine learning, which is data-based. And then what has happened in science is that the whole interest, so these are publications in computer science conferences, so the interest in the old AI has come down, and the interest in the new data-based AI has shot up. Okay. And so then another thing, so I'm just showing this, so this is like a classification of machine learning methods, right? We have supervised, semi-supervised, unsupervised, a lot of different things here. This is it's not important what we see here. What I want, my message here is there's a lot of different methods in machine learning, and neural nets is just one of them. And so I will show you also from my own work, there's lots of really good applications of many of these methods, and not every problem should be solved with a neural net. Nevertheless, I think we need to talk a little bit about neural nets, because that is the thing that is getting a lot of the mentioned currently. And so here we see a very basic schema of a neural net. And so the key thing to appreciate, I have some inputs on the left, I have some outputs on the right, then I have in one layer in the middle. Of course, I could have more. So those are called the hidden layers. And so that's also exactly why it's called deep learning. So it's deep learning because this is like a layer cake that can have many layers in the middle, right? So deep learning basically means it's spatially deep, it's not conceptually deep. The other thing that we can already see sort of from this idea here that I can have as many inputs as I want, I can have as many outputs as I want. And that is one of the real strengths of neural nets. But a lot of these other machine learning methods are way more defined. Right? Maybe I can have only one output, for example. Right? So in here you can configure this however you want. And then maybe the last thing, so how does something like this learn? Basically, I have a data set, right? Of course in AI we always need some sort of data sets to feed into the machine. And so my data set consists of some desired inputs and some desired outputs. And then learning basically means that based on the input, the net can predict the final output. And how does it learn? We basically put some little numbers here on these lines here that are called edges, so that connect these elements. And then what happens is basically we do an optimization process to find the best numbers to put on these edges to most reliably predict the right outputs with the right inputs. So key message, the learning of a neural net is basically an optimization problem. Okay, so, and what can we do? And this is the powerful thing about these neural nets. So for example, I could say numbers in, numbers out, right? So stock market today, stock market tomorrow. I could also say I do pixels in and words out, right? Because pixels are actually just numbers. Right? So I have this picture here of a cat, and then for the computer that is numbers, and then the output, of course, should be cat, right? And this is like a typical neural net output where it says highly likely a cat, but it could also be a dog, right? And so this is, of course, pretty old technology, has been around for a long time. But then some of the newer, more interesting applications is like from words to words. Right? That is your GPT. Right? I give you a prompt. I say, tell me a story about a rabbit, and then it will tell me a story about a rabbit. That's a mapping from words to words. Or of course from words to pixel. Right? That is the image generation. And because I think as architects you can also appreciate this is basically a symbolic arrangement. Right? So if I can put numbers in and again get cat out, that also means I can put in cat, and then the output will be the pixels that represent the cat, right? And that is, on a very basic level, how this image generation works. Okay, and so these neural nets have been around for a very long time. Basically, actually, since the beginning, since the 60s even. And so the question is, what has changed? Why is it so important now? And so I have basically a model with a very basic answer. First of all, there's a lot more data, right? So a lot of, basically that's what you need for this training is data, and through the internet a lot more data has been available. So what you see here is the growth in the number of websites on the internet. But you can also see that it's now flattening, right? So it's only a linear increase. So basically, the way I would see this is that basically a lot of the knowledge that can be put on the internet is already on the internet. And so from that we could conclude that maybe the rapid improvements in AI that we have seen recently, maybe they're not going to continue, right? Because I don't think this curve is going to exponentially continue in terms of the training data. And then of course the other thing is compute, right? There are data centers because we need, on the one hand we need a lot of data, but on the other hand we also need a lot of computing power. And so there I just want to mention that currently about 1% of global energy use is in these data centers. And 1/3 of that is blockchain. And then the last bit is the models themselves. So this is a chart that shows you how many of these units. So when I say units, I mean the circles. How many units are in the current neural nets? And so this is logarithmic, right? So this is like tens of thousands, hundreds of thousands, millions, etc., etc. And so you can see this is somehow also honored exponential. And so the current state of the art is 10,000 billion parameters, like for a GPU. GPT model. And I find that quite interesting because if you then think, okay, how many neurons does the human brain have? It's only about 30 more. So which means it's basically you need to go one more up. Right? So if this goes one more up, then you will have a neural net that has as many computational units as a brain. Do I think that this will lead to human-like intelligence? Absolutely not. Because of what I said earlier, there's no understanding of concepts, which I will demonstrate in a bit. But so, and this is now I will show you some example, and basically you're all familiar. So this is a GPT-3, very old now, from 3 years. I like it because of the content, right? So this is about philosophy, and so the prompt was, "Dear human philosophers, I read your comments on my abilities and limitations with great interest." So this is sort of reflecting on, I'm just a language model, I don't have morality, but I can reason, and so it's quite interesting. It does, but you can also start to see there is this phenomenon that's happening, right, where so you start with the sentence and then you basically try to predict the next sentence that is plausible. And then you take this sentence and you predict the next sentence that is plausible and so on. And it's always a statistical process, right? So as I showed before, it's 80% cat. And which means, which you might have also experienced yourself, that the longer these things get, the less plausible it is. Because you can just move away. So you start sort of in the area where things make sense, and then the more sort of random steps you take, the more away you get from something that is true, let's say. Right, and so now we get to this image generation. So, right, I did the thing, right, astronaut on horse on Mars, very happy, right, very nice, a convincing image of an astronaut on a horse on Mars. Although we can, of course, immediately say, yeah, but what is this horse breathing? Right, so there is sort of a meta level where this is not correct anyway, but okay, this was, I mean, I said this is what I wanted, right? But now comes the interesting bit. Then I said, okay, I want a horse on an astronaut riding on Mars. And it looks like this, a horse riding an astronaut on Mars. And so why is that? That's because the internet is full of images of humans on horses, and there are no images, or very little images of horses that are on humans. And I want to illustrate, this is really the difference is human intelligence. Right? If I ask you, please draw me a horse that's on a human, you can totally do it. Right? Because you do understand the concept of what up or down is, and you understand the concept of that something is riding something else, and you understand the concept of left and right, etc. These systems do not, right? Just don't. They just infer from patterns, right? And so that is one of the key limitations, and that explains also some of the other issues that I continue to highlight. But basically, I use this, and then I will to say, so fundamentally, if we want to use methods like this for architecture, there is a problem, right? Because how can I have a method to generate architecture that doesn't understand up and down and left and right? That I find problematic. And so then I did just some little play, right? I think I want a house shaped like an architect, where I thought, right? I thought about this famous picture from the 1920s where the architects draw up as houses. And so, okay, I don't know, right? Maybe this comes from a data set of many first-year design projects. I'm not sure, but then of course what's more clear is if I say architect shaped like a house, yeah, so white guy in a suit, that's an architect, that's the first thing. So of course there's this idea of bias, right? In this knowledge, so what these systems generate is just what's on the internet, right? And so the internet is not society, not reality. And then of course this idea that the architect should be shaped, I mean, if I give this prompt to design students and they come back with this, right, that's not going to be that's not going to receive a very good critique. Right, so, and again, so it's conceptual understanding selecting. But, and so now this is more the state of the art, GPT-4, GPT-4, sorry. That I find now more profound and interesting. So what's happening here now is, okay, so this is a picture from Kandinsky, and now we could, of course, say make me a picture of Kandinsky, but this is not what this is. So this is produce JavaScript code that creates a random graphical image that looks like a painting of Kandinsky. So you basically ask the system to generate computer how to make something. And so that was the big improvement in this year. So previously, if you said this, produce JavaScript that creates something that looks like Kandinsky, it was that, which is really not very convincing. While this, I would say, okay, it's still not exactly Kandinsky, but it's pretty close. And so that I think is already starting to emerge as a primary application of these systems, is to sort of support computer programming. And why is that? Again, because of course the internet is full of computer code, and especially full of little small examples. And apparently, I've just heard that this is a problem now, because any of you that program knows about Stack Overflow, right? You go to Stack Overflow when you have a problem. But nowadays people don't do that anymore. They just ask it to GPT. And so, therefore, if no more questions are being asked and answered on Stack Overflow, then this data source is now basically finished and cannot evolve anymore. And here's just another more expressive example, which is like, can you write a game in HTML in JavaScript? And yeah, so that works, and especially I think it's also no coincidence that they use JavaScript, because JavaScript is like super popular, and JavaScript is how you write programs on the web, right? So, as I said, basically whatever is represented well on the web works, but things that are not so well represented on the web, and for example, something like the classic canon of architectural design that every student will learn, that's actually not super well represented on the web, and what's much more represented is something like Scandinavian interiors and things like that. Okay, so from that I conclude this first section. So AI offers a wide range of methods to produce and to process and generate data, including computer programs. And so from a computer science standpoint, a computer program is also data. Database AI, so by which I mean neural nets, offers scalability and flexibility. So scalability, I can make it as big as I would possibly want, as I've shown you. Flexibility, I can do a lot of different things. I can input text, output images, whatever. But yeah, I say it's no distinction between right and wrong, but basically what I mean is no distinctions between any symbolic concepts, and that's why I say that all these current assistants are not intelligent in the conventional sense, because in a sort of everyday use of intelligence, we assume there is an understanding of concepts, what left and right is, what up and down is, etc. Okay, and so now what does generative AI mean for design? And now I've given it a little bit away, but I have a really nice example, I think. So this is actually an architect who I know from Singapore, and who is sharing his frustration. So what he is doing is he wants to generate what he says here, so a commercial design next to a shop house in Singapore that blends in with the heritage and culture, but stands out as modern and innovative. Yeah, now you can say maybe this is not a coherent design intent, right? But then his complaint is basically this all looks like Audi style. And it does, right? And why is that? It's because if you say, yeah, I want something sort of that blends in well and it should be sustainable, then the internet thinks, okay, if it's sustainable, then it probably has an organic shape and it probably has trees on it. And then you can see that somehow, sure, there is an idea of Singapore here, right, and shop houses, but it's not integrated meaningfully. So again, so basically, there is not only this bias in terms of that only white people are represented, there's also a bias in terms of what sustainable architecture is, or what architecture that is in a certain context is, etc. And then this reaches its high point, sort of with Philipp Schumacher, who says, okay, I'm Philipp, this is like apparently a screenshot from Patrick Schumacher, that's very important. And so he says, Zaha Hadid Museum, aerial view, high quality. And indeed, it kind of all looks like this museum in Korea. But if you are now an architect, and this is your design strategy, which he claims that it is, so he claims, I go through the images and then I give something to my design team, yeah, then you are dead as a creative architect, right? Because it's completely feeding on itself. Then your design team will make new images, it just look like the old images, and you put that again on the zine, and it just becomes this endless cycle that feeds itself. Okay, so now I want to show you what I think is one of the best examples of a generated piece of AI architecture, or maybe not. So let's see. So this is Matthias de Campo, who some of you might know, one of the leading proponents of this idea of AI-generated architecture. And so what he does is way more sophisticated than what I've shown you before. Right? This is not just typing things into Midjourney. So what's happening? So he has a data set here of elevations of modernist houses, about 1,000 elevations. And then here he has a data set of about 1,000 modernist plans. And then he basically trains two neural nets, one neural net that understands modernist elevations and one neural net that understands modernist plans. And so then you can generate new modernist-looking elevations and new modernist-looking plans. The problem is, of course, it doesn't fit together. Right? So there's still this conceptual issue that as architects, we think this should be connected, but of course, if you just say, I take existing elevations, make new ones, there's absolutely no guarantee that this will fit together with the plans you are generating. And so then there is this orthographic projection here, where you say, okay, I take some AI-generated elevations, I take an AI-generated plan, and I generate a building. Just let's jump to that, and so that's how this looks like. I mean, I actually like this project, but my point is, this is a human-made design, because a human chose some elevations and some plans that somehow make sense. And that is not, this supposed AI system cannot do it. So you need a Matthias del Campo to make this choice. And just as a technical note, I just want to show this. And so what this is using like something like a variational autoencoder. And what this allows you to do, here's a simple example. Say, okay, I have the triangle, I have the circle. And so because we have Corbusier, I have Mies. And then the neural net can sort of infer, okay, so what's maybe in between Mies and Corbusier. So there is a sort of interesting design potential here, doing this interpolation, right? And so that's also what he's doing, is sort of interpolating from these existing famous architects some new things. But of course, what comes out of it looks very strange, right? It looks very strange because, yeah, as I said, because the sections have been generated totally independent of what the plans are like, which is, of course, all against all the tenets of modern architecture. And then this is just, again, an illustration of that. So, to conclude this section, I wanted to show you, so this is some work by a student, master's thesis that I've supervised. So similar idea, so 4 modernist houses, but then saying, okay, let's actually have a 3D data set. And then we encode this 3D data set as graphs. And so what this thesis is about is trying to not just work in like images, so not just working in planar section, but trying to actually encode some spatial relationships. And so trying to say, okay, so what we actually want to learn is how in these houses, what the relationship is between like the walls and the ceilings and how they are connected. And then what you can do is can generate things like that. Which of course very easy to criticize. There's no program here, there's no materiality, there's no site. But at least I would say it is superior in what I showed you before in terms of the AI. So actually something 3D is being generated here. And you don't need a human to somehow curate sections and plans. Okay, and so from that we can conclude that, of course, so this two-dimensional generated AI can serve as a source of inspiration starting point. Sure, you can generate some images and as I said, use that as a starting point for a design. But it's probably not more than that, right? Because it's completely biased, it's potentially self-referential, and it lacks understanding. Then there is this still what people are interested in, and I'm also interested in, is this issue of 3-dimensional generation. I say that's still at the beginning. So yeah, there are approaches to this, but it's quite difficult. So we are basically what I'm saying, we are very far away to generate like a serious building design with the methods I've presented so far. And then we need the human, of course, right? We need these human design decisions to combat these issues that I've mentioned, like the image cliche, like the sustainable building with trees, the bias, and the self-referentiality. Okay, now we do a little shift and talk about the supportive AI. So that's where I position more in my own work. And so, not strictly speaking AI, so it's about, well, so I'm going to talk a little bit about optimization. And as I explained, optimization is kind of how these systems learn. So you can think about it as a part of AI or not. But this is what I did for my PhD here. And so the point was, let's look at structural structural optimization, energy use optimization, daylight, glare, and just about this, how can I find very efficient solutions? And people that are in this field typically said at the time, and actually still continue saying to this day, that you should do this as a genetic algorithm because they are superior and robust in every way. And so what I show here is that it's the worst. Right? So basically what you see here is at the bottom would be the best solution. And then this is how many steps you take. So basically 500 means I've done like, let's say 500 energy simulations or something like this. And so the game is basically to, in a small number of steps, to come very close to the optimum. And you can see that especially this genetic algorithm, and then there is also the simple genetic algorithm. So the GA, that is the Galapagos GA for our grasshopper users. The simple GA is just the GA that you would find in the textbook, like the most basic version. And they are actually the burst. Both of them are the burst. Then there's a lot of other options in between. And then there is this RBF opt, which is in a possum, that Peter kindly mentioned, which is the best. So if you want to do things like this, like optimized buildings, especially so where this really becomes powerful in this context where you connect this optimization idea with a heavy simulation. So maybe you run like a heavy energy simulation that takes 5 minutes. That's where RBF really shines. And so I'll just make 1 minute about how does this work. So this is basically a machine learning approach that says, first I'm just going to sample a little bit, so I'm going to take some random solutions, then I interpolate, so basically then I try to guess, and then the optimization works by, I'm guessing, so I'm predicting this is probably a good solution, so this is what I should simulate, then I simulate it, then I'm probably wrong. This is probably not going to be right, but I can basically learn from my error. Right? So then I know, okay, I was wrong, so let me update the model, let me guess again. And so if you guess 500 times, you continuously improve your guess. That's how you improve quickly here. By these more genetic approaches, it's kind of like quasi-random search. You're just manipulating your variables until you get somewhere. Okay, there was a very brief excursion on that. So other things we're doing, so now this is some work of my PhD students. I show this basically to me. This is how we should always work nowadays. So what this is we have some urban design here. Of course, we have parametric variance. So this is some development in Zurich. And then there is this dashboard here, which talks about the floor area, usable space, number of residential units, parking spaces, the profit I can make, but also sustainability criteria. And what we added in here is this idea of a surrogate model. So a surrogate model is basically a machine learning model that replaces a simulation. So in this case, a machine learning model that replaces the energy simulation. So what's here is like the energy used for heating and cooling. And the whole point is, rather than optimizing, this just shows you the information, and then you sit around the table. So the client, architect, urban design officials, and they can just make an informed decision together. And there's not a lot of research necessary. We can just do it, and we should always do it, right? We should make these things transparent and then make good decisions, right? And so rather than saying we just optimize, I think it's more about machine learning and AI can sort of support these kind of collaborative decision processes. Something else that I think is a very interesting application of machine learning is for material behavior. So this is some work which is about, at the ICD, we are using this self-shaping behavior of wood, right? So wood deforms under moisture, and basically we want to deform it strategically to get like two curved wood structures. And so obviously, in order to do that, you need to predict how it's going to deform, which is quite difficult, right? And especially it's difficult because, of course, every piece of wood is unique, right? And the uniqueness is sort of in the fibers, like how the wood is grown, how the fibers are laid out. And so this is about, these are some experimental results from some small pieces of wood, and this is how much they've deformed. And the line up here, this is like the engineering formula. So the engineering formula says, okay, they're all the same, first of all, of course, and it's also just completely wrong, because the engineering formula makes some very bad simplifying assumptions about the piece of wood. then the blue dots are the actual measurements, and then the red is what the machine learning model predicts, which is fairly accurate except for 2 points. And so in this case, the input to the machine learning model is basically pictures. Or basically, so it's about photographing the wood grain and then doing some image analysis on this wood grain to extract some higher level numbers that describe like the fiber distribution, and we're using that to predict. And then this is another, there's another step to this, where then we showed this to some wood engineers who said, okay, we can have a really nice, complicated finite element model, which you can see is much better. So this fits pretty closely. And so basically, so they made a finite element model based on our data, so using the actual measurements from the wood. But the finite model is still, the finite element model says all pieces are the same, right? And but the point is basically that you still have these deviations, right? So basically, what this machine learning is really good for if you want to work more with bio-based materials in the future, which is of course what we should do, right? Both for CO2 and for circularity reasons. Then our classical engineering models that we typically use to describe things like CompuTC will not work anymore, right? And then sort of a database approach can help, especially in situations where we don't even have a proper formula. And then something else, this I would say this is a very ICD application. So this is about the research. So this is one of the newest demonstrator projects. And of course, there's like 500, I think, of these digitally fabricated timber cassettes that are robotically fabricated. And if you do that, then you get to the idea, aha, so maybe we should collect some data here, and then we can make predictions. And so what this is about is just collecting the data from this process and trying to see if we can predict how long certain things will take. Right? So I have a certain cassette, and I know I have to glue it, I have to nail it, I need to move it around. How much will this take? And you can see it's somehow reasonably well correlated here. And so this is the big dream in our class of experts is this idea of co-design, where we design already with the making of the building in mind. And so there this can really help, because you can get very early on quite precise feedback, how easy this will be to build, how long it will take, etc. And so, just a little side note, so this was very recently completed at the University of Stuttgart. Sorry, not University of Freiburg. So University of Freiburg is the client. And so this is sort of an idea space. And basically ICD by now has this sort of series of these wooden shells, but I would say it's the first one that is pretty much a real building. So this is actually climatized, zero energy with a heated floor and a heat pump. It's usable all the way year round. Yeah. And as I say, of course, it's digitally fabricated. And then one of my PhDs has developed this sort of management software that let's say orchestrates, right? Because there's two robots, we cannot see the second robot. There's a second robot here, there's some humans here, and so if you do these kind of more complex processes, you realize that you need to have a software to manage it, so which is that. And I'm just showing this because, of course, if you then have a software to manage this human-robot fabrication process, then you also can collect the data that you need to do the predictions I showed earlier. So, of course, we can also just analyze things like how much time was spent on traveling and rather than actually doing things. And then finally, I have nothing to do with this, but I find this a very impressive result of the research cluster as a whole. So this is then the final step, right? So pavilion digitally designed, robotically prefabricated, and also robotically assembled. So here we have one robot that is placing the cassette, and the second robot is nailing the cassette. And so that's kind of what we're going for is this complete digital process, where you digitally design, but also then you have this kind of semi-autonomous, autonomous construction side. Yeah. As I said, this is mostly the domain of the control engineers, but I think again, of course, what our ambition is, of course, to extend this management framework, which for now is mostly in the factory, also onto the construction side. So this integrated process, and then once we have done that, we can make the same kinds of predictions, like gather a lot of data about the construction, make predictions of construction, etc. Okay, now different topic. So yeah, I don't have a lot of time, so I'm just gonna very, very quickly go into this. So started this. So we are looking at these graphs, which are called knowledge graphs, particular kind of graph. This is actually sort of the old school AI. You are actually all familiar with this type of technology. If you go into Google, you type Paris, you get the box, right? That says Paris is the capital of France, 7 million inhabitants. You should see the Eiffel Tower and the Louvre. It's this kind of technology, right? So this is some form of AI on the level of concepts, right? So of course you could go to GPT and ask, hey, what should I see in Paris? It will give you an answer, might be right, might be not right. If you ask Google about Paris, it's correct, right? The sites will be correct, the number of inhabitants will be correct, and that's because the knowledge is encoded in this kind of format. And so basically what we're saying is this is the right way to do BIM, because that is how information is represented to computers, this is how information is represented on the web, this is how information can be exchanged. And since this is a fairly old technology, so there's actually a lot you can do with it. So for example, this is an example where we are just asking, tell me how many cassettes I have that have a certain weight, inferring from the volume of the cassettes in the material. Right? This is just an example of how I should be able to ask questions about my BIM model. Right? How many doors that I have that have a certain width and also a certain fire rating and things like this. This is basically, if you decide to do your BIM like this, you just get it for free, right? Because there is a lot of technology to do things like that. So specifically, you can do this, which is querying, and then there is also the other thing, constraints. So I can also make sure, for example, I can make sure that all my rooms have a number, have like a room number and an area assigned, right? And this kind of technology just allows you to naturally do things like this. And so what we've done, in Grasshopper, we built a very basic prototype how this can work. So you kind of model a very basic building, then a graph gets generated, and we upload it automatically onto this website, that is GraphDB, where you can sort of see and manipulate the graph. And you can also do this kind of querying that I just mentioned. And then this gets fed back also in Grasshopper. And so, yeah, we say this is the right way to do BIM, and we have this very, I don't know, the ambition for in the next 10 years to really make this into a fully fledged working thing. Right. Okay, so these are basically the whole point of everything I've said in this section was to say there's a lot of things to AI. It's not just these generative images, and actually it can be super useful, but it's probably the usefulness is probably not really in generating these concept images. That's what I'm trying to say. And so AI can support multidisciplinary design decision-making with real-time feedback. This is what I said in the beginning, right? This kind of dashboard. It can check compliance with rules and regulations. This is this graph thing. Exactly. And now we get to the last thing. What does this now all mean for practice? And there I will show you now again some totally, we're going in a different direction in a way. So the first thing that I like to show is always this. So this is a book from 1986 from Germany, which says CAD, Automated Architecture. And so there's a whole book discussing about, oh my God, we're going to draw on the computer. What does this mean? Is the artistic touch of architecture now going to go away? Etc., etc. And there's some really interesting forward-looking stuff in there about using rules to automate designs and what the human designers can do, etc., etc. But there's this one guy who wrote an essay, who is this architect from Munich, who said the following. The text machine has quickly established itself in the daily use of architectural officers. So what he means is we do write our letters now in the computer. Despite these efforts, the computer-aided design machine will not become established in architectural offices. And I just show this because I think it's quite typical of the attitude of many architects to always say, this is just a phase, and this will never happen, right? And so drawing in the computer doesn't make any sense, right? It will never happen. And now we have this, right? Finch. Right, so which I can, that is also AI, right? So this is basically design automation, right? And so this is not based on neural nets. This is again just based on rules, based on knowledge on how apartments are typically laid out. And this is, I think, what the 30% is, right? So basically everything that is sort of rule-based, and a lot of architecture that can, of course, be automated and is being automated, and that is what Goldman Sachs is talking about. And to me, this is what architects should be concerned with, and not with midjourney. And then just to have another example here, so Giraffe, some of you might know it, so this is a sort of urban design tool from Australia where they have integrated a lot of information about like urban design regulations in Australia, so they can tell you on this particular plot, this is the distance you need to have to the edge, this is how much you can build, this is what you can build. They give you, similar to what I showed you on the dashboard, right? They say, okay, you can build that much, that means you have a floor area ratio of this, you can probably make a profit of that. And so they say, right, as you design and create, Giraffe works alongside you, calculating areas and ratios, laying out the parking, analyzing soil and managing data. Free yourself from boring. There's of course one way of looking at this is, yeah, this is all boring stuff anyway, and why would I have to do it? Why let the machine do it? The problem is that you have people like Chase, who says Giraffe turned a potentially hour-long sketching session and a day of back and forth with architects into a 30-minute review of concept I created using them. And so this really cuts both ways, right? On one hand, you can say, yeah, these kinds of methods, they automate the boring stuff, which is great. But on the other hand, a lot of the boring stuff is also the current business model of architects. And so I've basically, the implication is that the business model needs to change. And here's just another example of the same thing. So this is TestFit, a startup from the US, and I could show you more examples of similar stuff. But this is, to me, sort of the most complete example where they can, okay, you go to our website and you can, well, we basically will design whatever you need for you, residential, commercial. And of course, this works sort of on a flat site, right? This is not too complex. But this sort of implies maybe the role for architects is more for the special situations, like the urban infill or very complex topography, very special program. But if it's something like this, right, some residential development on a green field, yeah, right, this is done in 60 seconds, and it already outputs the BIM model. Then the final example, this is a little bit more speculative. So this combines basically this idea of rule-based architecture generation with the idea of prompting. Right? So there's now a prompt here that says, okay, I have a building here, it has a 3-story podium, and then there's parking, and there's a residential U-shape on top. So there's a text that describes it, and what is being generated is a BIM model. Right? And so this is basically works exactly like this JavaScript example. Right? So instead of saying make me a game, I can say make me a BIM model, and then it's not that not like in the Matthias de Campo case, right, where directly a design is generated. Here, from the prompt, basically some parametric rules are being generated, and then the rules generate this design. And so that's also, but yeah, I don't know. Right? So this I think is. This shows us that this idea of the language model is definitely very powerful for user interfaces. Right? And so now I go back to my graphs. But of course the problem, one of the problems with the graphs is, yeah, you cannot ask an architect to write this thing. Right? But you can use a language model to do it. Right? So you can say, hey, I want to know if my robot can lift the cassettes, and then the language model could generate the query, and then we can query the graph. And this is more or less what is happening here, right? Where we have the language model that understands sort of what the human wants, but then there is a whole rule-based engine behind that makes sure that the thing that is generated is somehow architectural and sensible. So to close out, I have some other quotes. So this is from this book Super Users by an American professor who thinks a lot about the future of the profession. And so he says, in the near future, the design professional will be an augmented and informed, so an AI architect collaborating with machines, or they call it competing with AI, and robots call it toast. So this means, as architects, yeah, we somehow need to engage with this technology. I hope I have to make this case quite clear, right? Because it's very difficult to compete, right? We cannot outcompete something like TestFit in the design of residential and office parks. So AI in architecture practice is more rule than database. So what I mean is, so the real thing is this rule-based generation, and this data-based image stuff that is more the distraction. And AI in architecture design means automation of routine activities, so things like parkings, factory layouts, etc., etc. But I also, there's a positive news in a way because it highlights artistic aspects, right? There are, of course, if I want something that is sort of culturally meaningful, adjusted to the site, very sensitive to its context, none of what I showed you can do it, right? So there's clearly still a role for the humans. But nevertheless, I think what this all means for the practice is that everybody should have like a basic computer science knowledge, and I tell every audience that I talk to that SUTD is the place where this is actually happening. And then there's also these new specialist roles, right? And so actually I talked quite a bit nowadays to like bosses of architecture offices in Germany, and they find this quite compelling. So the idea that you need some, right, not only do you need like a BIM manager, but you also need some people that understand all this type of technology and make it useful. Yeah, that I think is pretty convincing. And so finally, I like this, so The Death of Drawing. So this is a book by someone who is not a fan of technology. He doesn't like it, but he says, like, nevertheless, it doesn't, right? We are losing a lot here, we are losing the human touch, but it's happening, right? So we are in the midst of a transformation that will ultimately reshape architecture to an extent not seen in over 500 years. Very few architects appreciate the magnitude of the sea change. And so that's how I see it, right? So we have the wave. The wave is already here. And the only chance here is to surf the wave, right? And so you surf the wave sort of by knowledge, by knowing how waves function. And I'm looking forward to discussing it.